100 years of waiting, a century of mathematical predictions, technological innovation, and scientific perseverance. This is the remarkable story of gravitational waves, perhaps the most elusive phenomenon in our universe, and humanity's extraordinary journey to detect them. In 1915, Albert Einstein published his groundbreaking General Theory of Relativity, forever changing our understanding of gravity. While Newton had described gravity as a force acting instantaneously across distances, Einstein revealed something far more profound. Gravity is the curvature of spacetime itself. Matter tells spacetime how to bend, and spacetime tells matter how to move. This elegant framework made a startling prediction. If massive objects accelerate, they should create ripples in the fabric of spacetime itself, propagating outward like waves on a pond. These gravitational waves would carry energy across the universe at the speed of light, stretching and compressing everything they pass through. Yet Einstein himself was skeptical about whether these waves could ever be detected. The effect would be unimaginably small. Even powerful gravitational waves would distort our measuring instruments by less than the width of a proton. For decades, gravitational waves remained a theoretical curiosity, a mathematical ghost haunting the equations of relativity. The first serious attempts to detect these cosmic ripples began in the 1960s, when physicist Joseph Weber constructed aluminum cylinders designed to ring when struck by a gravitational wave. Weber claimed success, but his results couldn't be replicated. The scientific community realized that detecting gravitational waves would require something far more sensitive than these Weber bars. In the 1970s, physicists Rainer Weiss, Kip Thorne, and Ronald Drever independently began conceptualizing a different approach, using laser interferometry. Their vision was both simple and audacious. Build L-shaped detectors with arms kilometers long, where laser beams would measure infinitesimal changes in distance caused by passing gravitational waves. This vision would eventually become LIGO, the Laser Interferometer Gravitational Wave Observatory. But the path from concept to reality was arduous. For decades, scientists and engineers tackled seemingly insurmountable challenges. How do you measure a distance change smaller than a proton? How do you isolate your instruments from the constant vibrations of Earth? From trucks on distant highways to the subtle movement of tectonic plates? The original LIGO detectors, built in Hanford, Washington, and Livingston, Louisiana, began operations in 2002. For 8 years they listened to the cosmos and heard nothing but silence. The instruments, despite being engineering marvels, were still not sensitive enough to detect the whispers of space-time. Rather than admit defeat, the scientific collaboration embarked on an ambitious upgrade. Advanced LIGO would incorporate cutting-edge technologies, more powerful lasers, superior mirrors, and revolutionary vibration isolation systems. The detectors would be 10 times more sensitive than their predecessors. On September 14, 2015, just days after Advanced LIGO began its first observing run, the universe finally spoke. At 5:51 a.m. Eastern Time, both detectors registered a characteristic signal, a chirp lasting just 0.2 of a second. The signal was unmistakable. Two black holes, each about 30 times the mass of our Sun, had spiraled into each other 1.3 billion light-years away, converting three solar masses of energy into gravitational waves. For the first time in human history, we had detected ripples in the fabric of space-time itself. The century-long quest that began with Einstein's equations had finally succeeded. The announcement came months later, on February 11, 2016, after rigorous verification. The scientific community erupted in celebration. Einstein was right. Gravitational waves were real. This discovery marked not just the confirmation of a century-old prediction, but the birth of an entirely new field, gravitational wave astronomy. For all of human history, we had studied the universe primarily through electromagnetic radiation, light, radio waves, X-rays. Now, we had a fundamentally new way to observe cosmic events, especially those involving dark objects like black holes that emit no light. In this program, we'll explore the fascinating journey from Einstein's theoretical prediction to LIGO's groundbreaking detection. We'll meet the visionaries who persisted through decades of setbacks, the ingenious technologies that made the impossible possible, and the profound implications of this new window into our universe. Gravitational waves are rewriting our understanding of black holes, neutron stars, and perhaps even the Big Bang itself. The detection of gravitational waves represents one of humanity's greatest scientific achievements, a testament to human curiosity, ingenuity, and perseverance. It's a reminder that even the most elusive phenomena in our universe can be understood through the careful application of science and technology. Detecting such minuscule distortions would require instruments of unprecedented precision. This is where the concept of interferometry enters our story. The Michelson interferometer, invented in the late 19th century, splits a beam of light and sends it along two perpendicular paths. After reflection, the beams recombine, creating an interference pattern extremely sensitive to tiny changes in the path lengths. Rainer Weiss of MIT realized that a scaled-up version of this device could potentially detect gravitational waves. If a wave passed through such an instrument, it would stretch one arm while compressing the other, altering the interference pattern. In 1972, Weiss published a detailed analysis of such a detector, addressing the numerous sources of noise that would need to be overcome. Meanwhile, at Caltech, theorist Kip Thorne was becoming convinced that gravitational wave detection was not only possible, but essential for testing general relativity. Thorne began a collaboration with experimental physicist Ronald Drever, who had been developing innovative techniques for gravitational wave detection in Scotland. These three scientists, Weiss, Thorne, and Drever, would become the intellectual architects of LIGO. Their combined expertise in theory, experiment, and instrumentation laid the groundwork for what would become the most sensitive measuring devices ever constructed by humanity. Transforming mathematical predictions into a functioning gravitational wave detector presented challenges that many considered insurmountable. The LIGO project, formally established in 1984, aimed to detect changes in distance smaller than 1/10,000th the diameter of a proton, a level of precision akin to measuring the distance to the nearest star with an accuracy of a human hair's width. The basic design was elegant in principle. Two perpendicular vacuum tubes, each 4 kilometers long, with mirrors suspended at their ends. Laser light would bounce back and forth between these mirrors, creating an interference pattern that would shift if a gravitational wave stretched one arm while compressing the other. But the execution required overcoming staggering technical hurdles. Any vibration, from distant earthquakes to nearby traffic, from atmospheric pressure changes to thermal motion of molecules within the mirrors themselves, could overwhelm the tiny signal of a passing gravitational wave. The engineering solutions were as ingenious as they were complex. The mirrors, weighing 40 kilograms each, needed to be suspended by glass fibers thinner than a human hair, creating pendulum systems that isolated them from seismic vibrations. Multiple stages of passive and active damping were implemented to filter out environmental noise across all frequency ranges. The vacuum within the tubes had to be 1/trillionth of atmospheric pressure, one of the largest and most perfect vacuums ever created on Earth. Without this, even the random motion of air molecules would create unacceptable noise. The laser system needed to deliver absolutely stable power, as fluctuations could mimic gravitational wave signals. Construction of the initial LIGO facilities began in 1994 at two widely separated locations, Hanford, Washington, and Livingston, Louisiana. The separation was crucial. A true gravitational wave would pass through both detectors with a slight time delay, while local disturbances would affect only one site. This coincidence requirement would be their most powerful tool for distinguishing real signals from noise. As the millennium turned, the first version of LIGO became operational. From 2002 to 2010, the detectors conducted multiple observing runs, gradually improving their sensitivity. Yet, despite reaching their design specifications, no gravitational waves were detected. This wasn't entirely surprising. The original LIGO had been designed primarily to prove the technology, with the understanding that a significant upgrade would likely be necessary. The absence of detection did not discourage the scientists. Instead, it provided valuable operational experience and data on noise sources. Plans were already underway for advanced LIGO, incorporating everything learned from the initial runs. The upgraded detectors would be 10 times more sensitive, increasing the volume of space they could monitor by a factor of 1,000. Between 2010 and 2015, both facilities underwent comprehensive renovations. Nearly every component was replaced or enhanced. More powerful lasers, larger mirrors with better coatings, improved suspension systems, and more sophisticated control algorithms. The investment was enormous, not only in money, but in human ingenuity and perseverance. As advanced LIGO neared completion, theoretical models suggested it might detect between 3 and 100 gravitational wave events per year, primarily from binary black hole and neutron star mergers. But uncertainty remained high. No one had ever observed black hole mergers before, and their abundance in the universe was largely unknown. In August 2015, the upgraded detectors began engineering runs to test their systems. On September 14, 2015, while still in this testing phase and before the official observing run had even begun, both detectors recorded something remarkable, a clear signal that rose in frequency and amplitude before suddenly ending. The signal lasted just 0.2 of a second, but its pattern was unmistakable to those familiar with the predictions. Two massive objects spiraling together, then merging. Initial automated alerts flagged it as a potential detection, but the scientists remained cautious. They spent months rigorously analyzing the data, checking for possible instrumental artifacts or environmental disturbances, and comparing the waveform to computer simulations. The signal matched perfectly with Einstein's predictions for two black holes, one 36 times the mass of our Sun, the other 29 times, merging to form a single black hole of 62 solar masses. The missing 3 solar masses had been converted to energy in the form of gravitational waves, releasing more power than all the visible light in the observable universe during those brief moments. On February 11, 2016, the LIGO Scientific Collaboration and Virgo Collaboration jointly announced to the world gravitational waves had been directly detected for the first time, a century after Einstein's prediction. The announcement marked not just the confirmation of a key prediction of general relativity, but the birth of an entirely new field, gravitational wave astronomy. The achievement represented the culmination of decades of work by thousands of scientists and engineers across the globe. It vindicated the vision of Weiss, Thorne, and Drever, who had persisted despite skepticism from many in the scientific community. and it opened a new window onto the universe, one that would soon reveal wonders that even Einstein himself could not have imagined.